In this video, we'll discuss the basic version of stochastic gradient descent, or short SGD, which is the foundation of all commonly used optimizers in deep learning. We'll also discuss the batch size, which governs how many data points to use in each of the steps of SGD. Let's dive right in. Stochastic gradient descent and mini batch sizes. So we've seen this batch version of gradient descent before, which can be concisely written like this. First, we initialize a parameter vector, and then we iterate this update loop in which we compute exact gradients g by using all the n data points and computing the gradient of the losses with respect to them. Then we use these exact gradients, multiplying them by the learning rate and subtracting the result from the current parameter vector theta. Now for nomenclature, methods that use this entire data set to compute the gradients are called batch gradient descent or also deterministic gradient descent methods. And now let's contrast this batch gradient descent setting to the stochastic gradient descent setting that we want to talk about more here. And stochastic gradient descent, we're going to abbreviate by SGD. So this SGD algorithm is almost identical to the batch gradient descent setting, except that we have this step here where we sample a batch or mini batch of m data points from our data set, and then we compute this approximate gradient g hat based on these m data points. And the rest of the algorithm is identical. Now, just for nomenclature again, methods that use mini batches of data points to compute the gradients are called mini-batch or stochastic gradient methods. And actually by now, because in the deep learning literature, nobody really uses batch gradient descent anymore, somewhat confusingly, people tend to call a mini-batch also sometimes a batch of data. So if someone says my batch size is k, then that with respect to this nomenclature means the size of the mini batch is k, and it doesn't mean that they do batch gradient descent. All right, so this was stochastic gradient descent in a nutshell. And now let's look at why this is actually a good idea to subsample the data points and compute approximate gradient with respect to those. So the first reason that this is a good idea is that there are actually diminishing returns in using a lot of data points to estimate the gradient. And this is because the error in estimating the mean of a distribution given m samples actually is only reduced by the square root of m. So if we have m samples, z superscript I, from some random variable, z, and z has a standard deviation of sigma, then our standard error in this estimate of the means of these samples, zi, actually is the original standard deviation not divided by a factor of m, where we're based on m samples, but only divided by a factor of square root m. So we have less than a linear return for our number of samples. For example, if we have 100 times more samples, then the noise is only reduced by a factor of 10. And well, typically, if we have 10 times less noise, that doesn't mean that this would speed up our optimization by 100 times. Maybe it would speed it up by 10 times, but typically it's a good idea to rather do more iterates with more noise. The second reason that stochastic gradient descent is a good idea is that there is actually often redundancy in the training set. As an extreme example, think about the case where all the data points would just be copies of each other. And then the gradient based on a single data point would actually be already exactly the right gradient based on all the data points. And in practice, of course, well, it's very rare that we have exact duplicates, But especially early on in the optimization, small mini batches already tend to point in the right direction, and most data points point in the same direction as the mean of the gradients of all the data points. So based on just a few data points, you can already make progress in the right direction, and you don't need to look at all the data points in order to go into exactly the right direction, because this is only exactly the right direction from your current point of view anyways, because this is a local gradient step. And these two reasons taken together actually often imply that SGD makes faster progress by just updating a lot more frequently than batch gradient descent. So let's do an example. If you can, for example, you have a data set of 1 million data points, and you run mini-batch gradient descent with, say, a mini-batch size of 64. Well, then by the time that you have a single update step with batch gradient descent on 1 million data points, you already have something like 15,000 update steps of stochastic gradient descent with a mini-batch size of 64. And in these 15,000 update steps, because of the redundancy in the data, and because of the fact that based on relatively few data points in the beginning, you already go in the right direction, you have already made massive progress in this time that it took to do a single step of gradient descent. So that's why stochastic gradient descent is actually a very good idea for a large data set. All right, so we're going to use mini-batch gradient descent, but how are we going to actually choose this mini-batch size? Because mini-batch gradient descent is really a generalization of gradient descent. We could just set the mini-batch size to the whole data set, and we would just get exactly batch gradient descent back. So it's all about how to set this mini-batch size. And there, one thing to take into consideration is that modern multi-core architectures, such as GPUs, are heavily optimized for large matrix multiplications. And they're actually often underutilized if you use too small batch sizes. So one common heuristic is to make the batch size as large as possible to actually get a bigger speed up of your matrix multiplications. And as large as possible, that means as large as your memory constraints actually allow. So as large as you can store on your GPU. And that's why it's actually important to think about things like the memory complexity of storing your network and of doing a forward and backward pass visit. So I just argued for having as large a batch size as possible. However, I'd also like to note that it has been observed that small batch sizes have a regularizing effect. And that is because basically they just add noise to the optimization, which then could lead to a wider local minimum where you generalize better. Finally, there's also an interaction effect between the batch size and the learning rate. So smaller batch sizes typically require using smaller learning rates, because if you have a small batch size, that will lead to a large noise in your gradient estimate. And if you then do a large step along this very noisy estimated gradient, then that might just lead to a region with very bad performance. And more specifically, it has recently been argued that there is this one-to-one relationship between batch size and learning rate, and that if you divide your batch size by a factor of k, then you should also divide your learning rate by a factor of k to get the same behavior. Now, there's also a subtle issue in which data points you actually put into your mini batch. Not how many, but which data points. So take as an example a case where you have some blood samples that you classify, and these blood samples are arranged successively by patient. So your first data points come from patient 1, second set of data points comes from patient 2, third one from patient 3, and so on. And if you would, for example, just take the points from the ith patient and put them into the ith mini batch, then the updates based on each of these mini batches would actually be biased and potentially point in very different directions because, well, maybe different parameters would be good to predict the individual outcomes of the individual patients. So you wouldn't actually get an unbiased estimate of your gradient by each mini batch. In contrast, the standard solution is to just balance your mini-batches by approximately to get an unbiased estimate of the gradient by simply randomly shuffling all your training data. So you typically do one shuffle of your training data, and then you iterate over that shuffled list. And that is actually more efficient than at each point drawing uniformly at random from your data set. And in fact, iterating over all your data points once using SGD, that is called an epoch of SGD. So an epoch touches every data point once. All right, so this already brings us to the end of this video. And as always, I'd like to leave you with some questions. So I encourage you to pause the video here, think about them to activate the material. Thank you, and I'll see you in the next video.